is section 3.2.1, the image problem. All right, so let's assume that we have an infinite conducting plane and we are going to say that the plane is held at a potential of 0. That's because it's a grounded plane. And let's go ahead and just for convenience set this on the xy plane. Y, x, z, and I am going to have a point charge that lives above the plane on the z-axis at some height d. So, what is the potential in all space above the plane? That's the problem. Okay, so let's see if we can figure out what that is. So maybe the first strategy would just say, all right, well, we have a point charge that exists on the z-axis. The point charge creates a field, and we can calculate the potential from a point charge. But the point charge will also induce some sort of charge distribution on my conducting plane. So it's not entirely clear what we should do just off the bat. All right, we're going to take advantage of what we said in the last video, which was if you find a solution to the potential, it is the solution to the potential. All right, and we're going to say that there are two requirements for this potential. One of the uniqueness theorems says if you know the boundary conditions, if they're correct, then you're good to go. Okay, so my boundary conditions the first one is that at the plane, or at z equals 0 where the plane lives, the potential must be 0. And as I go infinitely far away, I guess infinitely far away from the charge, just that potential must be 0. Okay, so infinitely far away just means x squared plus y squared plus z squared is much, much bigger than the position of my point charge. Okay, those are the conditions that must be met. Okay, and there's no way that I would, without having learned of this strategy that we're going to talk about today, that I would expect you to guess what the solution is. But let's go ahead and create an entirely different problem. Okay, our entirely different problem is going to say, all right, I have the same coordinate system, x, y, z. Right? I still have my point charge, a distance d above. All right, I should mention that we're going to assume this is a positive charge, and it's a distance d above that plane. Let's go ahead and say, what would happen if I put another charge down here of the opposite sign and the same distance away from that plane d? All right. I don't have a conducting plane in this case. I just have my point charge that I know exists, and I'm pretending that there's another charge down there. Let's write what the potential is at all points in space there. Okay. My potential everywhere in space is the sum of the potentials from each of those bits Okay, I have the potential from the positive charge. That is going to be x squared plus y squared plus z minus d squared. Okay, then I have to add the next potential, which is minus because of the sign of that charge, minus q, x squared plus y squared plus z plus d squared. Okay, the pluses and the minus comes from the plus d and minus d come from the fact that one is a positive z value. This one's a positive z or positive d value in the z-axis, and one's a negative. So when you take your script r vector, you subtract those two vectors. Okay, now let's ask ourselves, what is the potential at z equals 0? All right, let's plug it in. 1 over 4 pi epsilon naught q over x squared plus y squared plus minus d squared, so plus d squared here, minus q over x squared plus y squared plus d squared. Okay, well, those are the exact same terms. That's 0. Okay, perfect. First condition is satisfied. All right. Next condition. What is v when x squared plus y squared plus z squared is much, much bigger than d squared? All right, I can expand this z minus d or z plus d out, and then I'd have a term that has x squared plus y squared plus z squared in it. Those are just going to be bigger. All right, let's see if I can. 1 over 4 pi epsilon naught q x squared plus y squared plus z squared minus 2 dz plus d squared. Okay, we have a similar term over here. X squared plus y squared plus z squared plus 2zd plus d squared. All right, but really this denominator is pretty much just that. It's not, it's approximately equal to that when d is really small. So again, I can rewrite this, I don't have space right now, but rewrite it as just equal to the square, something in the denominator has x squared plus y squared plus z squared. Right? Again, that starts to look like this expression. Those terms are the same. So the potential becomes 0. All right. So this expression we wrote for the potential had nothing to do with the fact that there was a conductor on the xy plane. But because it satisfies the boundary conditions that we needed to satisfy, it must mean that that is the potential, that is the solution to the potential. Okay. Now, it's important to note that this is only the solution to the potential above the xy plane. All right. Everywhere above the xy plane, I don't know how to draw this very well here. Everywhere above the xy plane, this is the solution. Okay, so for z greater than 0, because you cannot put these imaginary charges in regions of space where you want to evaluate the potential. Right? These imaginary charges are called image charges. This is why this is called the image problem.